or so to go, but we'll go ahead and get started anyway. So once again, my name is Arun Prakash. And of course, this is course 74, Structural Analysis 2. And just to get some idea about my audience here, let's maybe from a show of hands see how many of you are senior students. Most of you, okay. And anybody, junior students, I guess. Okay, a fair number. Any sophomores, graduate students? Yeah, there's always a few graduate students. And anybody from outside the structures area? Okay. All right, sounds good. So did I miss anyone? Doesn't look like it. Okay, pretty conventional class then. All right, so I'll go over the syllabus a little bit quickly, and then we'll get into the material straight away. As it says, my contact information on the syllabus is given here. I'm planning to hold my office hours on Tuesdays and Thursdays, 3 to 5, and we have a TA for the course, my PhD student who has just actually defended, so she's Dr. Hui Liu, and she'll be holding office hours on Monday, Wednesday, Fridays, right after the lecture, essentially from 3 to 5 p.m. in civil engineering also. Other than that, if you need a time to meet, feel free to email us. We can always work something out. Anybody here for whom none of these office hours work? Okay, all right, good. So hopefully you can find us whenever you need us. We do have a course webpage that I'm displaying up here. Just set it up this morning. So basic information here, syllabus is there. I'll be posting lecture handouts, so might as well send that around here. So you can take one and pass along. Sorry, I think it might be better to give it onto the lines. Okay. So I'll do it this time this way. It's the second handout. Those of you who had a course with me before probably have seen things like this. How many of you have had a course with me before? Okay, you. All right. So I'll be posting these lecture summaries, and I intentionally call them summaries because these are not supposed to be full lecture notes. You're supposed to supplement them with your own handwritten notes, attach a separate sheet of paper as needed, and also read the textbook. I'll come back in a bit. The textbook for this course is probably the same textbook that you use for 371, Hibbeler Structural Analysis. This is the 9th edition, but if you have an older edition, that's perfectly fine. The material doesn't change too much between those editions, and it's mostly the problems and the numbers a little bit that change. There's a few other recommended textbooks also mentioned on the syllabus. Maybe I should open the syllabus. Let's see. All right, so there's some description about this course, and one thing I do want to point out is this long list of prerequisites. So since this is probably the most advanced course in structural analysis that you will take as an undergraduate, it does build upon a lot of your expertise on the previous courses, namely 371, of course, structural mechanics 270 that you probably took back in sophomore year, and basic things like statics and dynamics, mechanics of materials and physics and math and all that stuff. So I think the initial maybe week or two of the course is going to be making sure that everybody is on the same page in terms of the prerequisites. If you have any concerns about any of these prerequisites, come talk to me as soon as possible, and then we can try to work something out. Specific goals for the course on the next page. Essentially, this sort of revolves around the key topics in this course. In the previous course, say 371 or structural analysis 1, you might have learned basic techniques of structural analysis, mostly for determinate structures. Did you guys see indeterminate structures back in 371? Some indeterminate structures. So here, what we're going to learn is a slightly different way to approach analysis problems. These are based on energy methods, which is basically the first topic up here, principle of virtual work, analyze different types of structures. We get into a method called the force and flexibility method. This is the one that you've probably seen in a simpler form for determinate and indeterminate structures. And then the main focus of this course is going to be on this topic 3 up here. This topic 3, which is the displacement or stiffness method. And in this displacement and stiffness method, we will make a pretty heavy use of a computer program, essentially MATLAB, where you won't have to program, but I'll give you sample MATLAB codes to be able to do simple structural analysis, for which you do need to have some basic knowledge of MATLAB. And I know that some of you may not be very comfortable with that, which is perfectly fine. We'll work through that, and I'll do a few sessions on basics of MATLAB as well to be able to, for you to get some experience with how to run those codes and how to analyze the structures. And finally, we have approximate analysis methods. This is sort of the brief list of topics. I've listed one last topic on an introduction to finite element methods. This is a method that is applicable to not just the structural frames and those types of structures, but also in general, any structure that can be used. So let's see if we get time to get there. Any questions so far on any of the topics or things, or contact hours or anything? Okay, so let me get into the grading basis then. There's going to be a few homeworks, pretty much one every week, but I'm going to do homeworks a little differently than what you might be used to. It works pretty fine. I'll talk about that in a bit. There will be 4 quizzes over the duration of the semester, and initially I was planning to hold those quizzes right here in class on Friday, but looking like it looks like we're going to be a really tight fit in this room, so we might have to move it to an afternoon set or evening exam type of quiz. So I'll still I'll figure that out and I'll let you know. But the dates would be these. These are Fridays of every 3rd week into the semester. So please do make a note of that. If there's any conflicts, and let me know as soon as possible. There's final exam, 25%. That brings us the total to 100. And there's going to be in-class small activities from time to time, which is basically just to make sure that you are participating and following what is being covered. So that's a bonus over and above the 100%. So that's sort of the grading basis. Like I said, I'll come back to the homeworks. And maybe that's a good point to distribute this out. Sorry. So this is the first homework, which is basically all based on the prerequisite courses. You should already know most of this, all of this material. Anybody who's missing a handout in the back? Yeah, it should hopefully get to you. We'll have to figure out a better way to do this. So I have a few extra copies of the syllabus here. Other than that, I think all the handouts should be somewhere in the back. All right, so let me talk a little bit about the homeworks. As you can see, it says there's two parts to it. Essentially, it's the same homework, just you need to submit it in two parts. In part one, you make your best effort independently without any external help, quote unquote, and doesn't it doesn't matter if you get the problems right or wrong. Okay, just make your honest, independent effort, and then scan and submit your homework to the Blackboard website. I've given some directions here on how to create a PDF file if you don't, if you haven't had that before. And then this part one would be due on Friday. And on Friday itself, we'll post the solutions to this homework. And even though I'm calling it a homework, I sort of refer this to as a practice quiz. It's a practice for the quiz that comes in every third week in the course, and actually practice for everything following that as well. So part two is basically where you take your solution from part one and looking at the posted solutions, try to compare your solution to the posted solution. And as long as you correct any errors that you might have made in your own solution, and I think I added a few more points in here, like list the most important concept for each problem that you think you learned from doing this problem, and briefly comment about how you would cross-check your own solution or the posted solution. So this is just part two is basically making sure that you go back and look at your own solution from part one. And then you need to just upload the revised PDF back to the web page. Sorry, Blackboard web page. And the way that we are going to grade this is part one is 10 points, where again, as I said, do it independently. Doesn't matter if you get the problem wrong. If you made an honest effort, you're going to get full points for that. Part two is 5 points, where we look at your revised solution. If you made any errors, correct them, comments on what we learned and all that stuff. And then 1 point for presentation, for a total of 15 points for each homework. So there will be 10 weeks, 10 homeworks through the semester, 15 points each. That's the 15% of the grading basis. Make sense? Okay. Any questions on this? No? All right. With that, I won't get into the actual problems right now. I'll let you guys think about it, and if you have any questions, please do post them on the discussion forum that's on the class web page. We and I will be actively participating in this discussion forum. So if you need a question answered quickly, this is probably the easiest way, rather than sending me or her an email, which then I end up answering the same question for more than half the class again and again. It's easier just to take questions and respond to them on this discussion forum. And I would also encourage you all to participate in that discussion forum to try to answer each other's questions as much as possible. So other than that, that's basically the logistics and the administration of the course. Again, any questions on logistics and stuff? All right. So if not, then we'll get into the material, and I'll refer you to the first handout page that I have up there. Um, and I think I'll have to zoom out a little bit. Let's see. Okay. I think that just about fits. Right, thank you. Anybody else need a handout in the back? All right. So I think today we'll just keep it fairly simple and straightforward. Basic introduction type material. So as we all, or as you all know, structural analysis is basically trying to determine how a given structure responds to loads and any type of stimulus to the structure itself. The response, of course, what do we mean by response? Basically, we need to find the external reactions given loadings, given boundary conditions, given the structure, given supports. We want to find what the external reactions are, first of all, and what are all the internal forces in terms of, say, shear force, bending moments at different points in the structure, what are the stresses, what are the strains at different points in the structure, and that's essentially what structural analysis is. We try to analyze a structure for given loads and boundary conditions and so on. I would also point out here that structural analysis, in a more general sense, also involves dynamics, right? What you all, or what we all have studied until now, are mostly static conditions, like given a structure, given load, how much is the, say, the deflection, or what is the shear force at a certain point, or what is the bending moment at a certain point, at a specific instant of time, or without taking any dynamics into account. But here's the question. If I have, say, a cantilever beam fixed at one end, if I apply a tip load here, suddenly, let's say maybe I take a mass and I place it gently here and then suddenly remove my hand. That pretty much amounts to applying a load at this point at, say, time equal to 0, and then just seeing what happens. So what do you think is going to happen if I apply a load, or if I place a mass at this point and suddenly leave it? What do you think would happen? It would oscillate, right? It would, and maybe another way to think of that is you deflect the structure initially a little bit and then let it go. And since this is not a very stiff structure, it doesn't oscillate much, but it does oscillate a little bit. And of course, in real life, structures are much stiffer and they will oscillate under load. So technically, dynamic response of a structure is also structural analysis, but it has a whole separate course, an advanced graduate level course called structural dynamics that those of you who might go on to graduate school might see. We will, of course, not be getting into dynamics in this course. We'll keep things simple, static. First of all, of course, we need to get static analysis figured out. The other part of this statement here is, when we talk about response of a structure, we are talking about response of its components, response of the material that the structure is made up of. And up until now, most of you, all of you, have seen pretty much linear, elastic response of the materials, right? our analysis methods typically restrict ourselves. We restrict ourselves to linear elastic analysis, meaning there will not be any damage, and we are assuming that there will not be any damage under normal loading conditions. Of course, if you take a structure like this cantilever beam, apply a big enough load, it will break. And that breaking is a nonlinear response of the structure. So once again, we will not get into nonlinear response, but this is something that you obviously need to keep in mind. And there's other issues about things like stability. Anybody know what stability refers to in structural analysis? When I say, go ahead.
Buckling.
That's right. Buckling is related to stability. So essentially, what this means is that I have this column, let's say, perfectly straight. I apply a load on the top, a small load on the top. Since it's perfectly straight, there's not going to be any deformation sideways. It's going to carry this load as it is. But if I keep on increasing that load, at some point, the column is going to buckle out of plumb. And that is a stability problem. So essentially what's happening really is that up until a certain amount of load, the structure was stable. But as soon as we reached what is called the Euler buckling load, at that point, the column buckles and it becomes unstable. So it is again a advanced concept, but these are things that you will learn as you go on to practice, and also as you go on to graduate school. So, but again, we will not get into these types of details. Let me talk a little bit about where all this fits into your education, into your big picture. Obviously, structural analysis, as you all know, is needed when we are, say, taking on a big construction project or a design project. Here I give you an example of a bridge. If I have an opening and really the design problem is, what is the structure that I'm trying to solve? Or what is the structure that I'm trying to build here? And the way we normally approach this is we come up with preliminary designs, and we analyze those preliminary designs, we refine the design, and we keep on repeating this process. So I won't again get into the details of all those processes. I'm sure you understand where this fits, but the idea really is that structural analysis, the problem of structural analysis comes in where you have a preliminary design in hand, you know what materials, what members you are choosing for different beams, columns, and slabs and all that. And then you want to check whether this preliminary design satisfies the requirements that you might have set for the structure. So essentially that's where it fits. Quick comment here about something about the design process itself. Now, design, as I said, is a much harder problem than analysis, but normally we don't approach it in that sense. Design is an inverse problem. Inverse problem meaning given like an empty valley, the question really is, what is the structure that would satisfy all these conditions, that would be able to take this load, that would be able to survive this amount of earthquake, this amount of wind load, this amount of snow load, and so on, last for, say, 50 years or whatever. So really, it's an inverse problem, whereas structural analysis is a forward problem. Given a structure, given the loads, how does the structure respond? Right. So now, technically, design is an inverse problem, but that's usually so hard to solve that we frame it in different terms and come up with simple simple preliminary designs, and then refine them using analysis. All right, so this is just a warm up of where we're headed. So, like I said, uh, the problem of structural analysis fits into the big picture with design and all that. But if we focus on the problem of structural analysis itself, what 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 do we do? How do we solve a structure? Let me talk a little bit about that. So normally, what we have in structural analysis problems is we are given a structure, either say this type of a frame building or a truss or any other structure. We are given loadings, dead loads, live loads, any transverse loads, and so on. We are given boundary conditions, meaning supports, so so that we can ensure equilibrium, and we are given material properties of the structure. So these are the four sort of things that are given usually to us in a structural analysis problem. And what we are trying to find is all of these things: external reactions, internal stresses, as I mentioned. In general, we are also trying to find stresses and strains at different points of the structure. Now, in building frames, we don't really get into that much detail about trying to find stresses and strains at different points. But by looking at the moment capacity of sections, we can judge whether this amount of stress and strain would be acceptable or not. And other than that, we are trying to find deflections at different points of the structure. How do we do this? We solve certain equations. We solve equilibrium equations. Of course, we need to have sum of forces, sum of moments equal to 0 at each and every point of the structure. That's the important part of that statement. Equilibrium, of course, means sum of forces and sum of moments has to be equal to 0. If I have, again, my cantilever beam with a tip load, the vertical force down here is the same as the vertical reaction up here. This is causing a moment about the fixed support. The fixed support is causing or creating a moment to resist that. The structure as a whole is in equilibrium, meaning sum of forces and sum of moments are 0 for the structure as a whole. But the more important statement is you pick any part of that structure. If I try to imagine like this cantilever beam load here, try to imagine a small portion of a beam here, or here, or here, or some cube of material here. Each and every small piece of the structure is in equilibrium. Only then is the entire structure in equilibrium. Make sense? Right. So, and the way to express these types of equilibrium equations really is through ordinary and partial differential equations. That's essentially what we solve when we do structural analysis. We solve ordinary and partial differential equations. What is compatibility? There again? It's related to displacements. When I say compatible, it means that the structure, the deformation of the structure has to be compatible with at each and every point with it. So for example, I again have a cantilever beam with a tip load. The deflection has to be continuous line, right? In addition to that, deflection being a continuous line, the slope has to be continuous, right? I cannot have a sudden kink in the structure at any point. And if I have, say, an indeterminate structure, I have a cantilever beam with a support here. Is this determinate or indeterminate? Indeterminate. Because 3 reactions here, 1 reaction here, 4 unknowns. And I cannot solve this just using equilibrium, right? So the statement of compatibility there would be that the displacement at the point of this extra support has to be 0. Right? This is hopefully what you've seen before in 371 when you solve indeterminate structures. So compatibility is the statement that the structure, when it deforms as a whole, has to be compatible with the rest. Among all its parts, it has to be compatible as a whole. Material relationships, of course, need to be satisfied. Like I said, we are going to restrict ourselves to linear elastic material. But of course, nothing is in the universe is linear elastic. Let me ask you this. Once again, cantilever beam, tip load. I apply a load P and I measure a displacement delta, right, at the tip. If I apply load 2P, what would be the displacement? 2 delta. If I'm assuming a linear elastic material model, then apply P, displacement is delta. And if you apply 2P, displacement is 2 delta. 10P, 10 delta. 100,000 P, 100,000 delta. Meaningless, right? So linear elastic material models, of course, have their limits. You have to, as an engineer, judge when does that linear elastic limit break down. Most of the codes, most of the computer programs, the analysis programs that rely upon linear elastic material models would be just happy to give you a response, say 10,000 times the allowable limit, and they'll say 10,000 times the displacement. But as an engineer, of course, we need to judge when that is applicable. And finally, we also need to make sure boundary conditions are satisfied. That if I have a fixed support, it doesn't rotate or anything like that. So this is basically the overall statement that given certain things about a structure, a loading, boundary conditions, so on, these are the concepts that we use to solve them. These are the equations that we use to solve them. And primarily, we have these two types of methods for analysis: a force or flexibility method, and it's very related to how you solve indeterminate structures. Some of you might have seen that before. And the other, displacement or stiffness method, is what we are going to learn in this course, maybe towards the second half of this course. So all these methods sort of work well for these frame type structures or beam type structures. But in general, when you have many or much more complicated structures, how do we go about it? If you have, say, a structure like this, anybody know what this is? The opera house, very complicated shell structure. Nuclear cooling towers, a dam. These are not beams or frames or plates, or these are not slabs or something that we can simplify and apply our conventional structure analysis techniques that you might have learned till now. How do we solve these things? So the idea here is that no matter how complicated the structure is, the underlying governing principles of structural analysis remain exactly the same. What do we use? We use these 4 principles to solve even those complicated structures. Every structure better be in equilibrium, better be compatible, better satisfy its own material relationships, and better satisfy its boundary conditions. But the ways or the methods that we use would be much more general than these flexibility and displacement methods that we normally use for frame structures, right? So, a common example to solve these types of problems is the finite element method that let's see if we can get into towards the later half of this course. Any questions on anything so far? It's basically, I'm just trying to set up the stage to get into some technical material now. No questions? All right. So if there's no questions, let's do an in-class exercise. So here, what I would like you to do is to take a piece of paper, write your name on it, and basically answer these 3 questions. And probably I should have asked this a while back. Those of you sitting in the back, can you see the font size and all that? It's visible? Oh, good. So let me, just for the benefit of everybody, state the problem. We have this beam structure. It's made up of two parts, which is a part that goes from A to B and then B to C to D. At B, I have an internal hinge in the beam, and at A, it's a fixed support, and in the middle of the second half, we have this load P applied to the structure. So the first question is this structure statically determinate or indeterminate? And to try to analyze this structure, you need to draw the shear force and the bending moment diagrams, and then based on those diagrams, draw approximately the deflected shape. So take maybe 2 or 3 minutes. Try to get, don't worry about the numbers or anything, but try to get a gist of the solution in place. And then I'll give you another minute to discuss with your neighbor and see, and then we'll try to solve this problem together on the board. Right, so let's take another minute, and then you can discuss with your neighbor after 1 minute. All right, so even if if you have not finished the problem, don't worry about it. I think the idea here is to make sure that you've had a chance to think about the solution and possibly formulate a method that given enough time, you can complete it. But take maybe another 30 seconds or a minute to compare your work with somebody sitting to the left or right or to the front or back, and see if you got the same answer for at least the first part. Is it determinate or indeterminate? And then see if you came up with same reactions or shear force diagrams and so on. Go ahead. Compare notes.
I was about to grab the move, but what if there's from negative was no, I just because I think it has no, it's not smaller process, but of course it's like when you pick on this side, this side wait a second, I think that's not right. I think his is right.
All right. All right. Let's bring it back, everyone. So, what's the verdict? Determinate or indeterminate? Determinate. And anybody says indeterminate? Okay. So let's see. How do we figure out whether it's a determinate or indeterminate structure? What makes it determinate or indeterminate? How do we even go about deciding whether it's determinate or indeterminate? There you go. So yeah, absolutely. A number of unknowns, number of equations. If number of unknowns is greater than the number of equilibrium equations that you have to solve for them, indeterminate. Right. So let's see if that helps us decide in this case. Since in this case the structure actually has an internal hinge, it means that the structure by itself, without the supports, cannot be in equilibrium since it has an internal hinge. So the logical thing to do there would be to separate out the structure into two parts, and I'll show you maybe even three parts. And no matter how you do it, if you do it consistently, you will get the right answer. Okay, either two parts or three parts. So let's see. If I take the left part of this structure, part from A to B, and the right part B, C, and D, and I apply my load P out here, I'll say there is a dy, cy. Since there is a cy pointing up on the right hand side, the force cy, which is an internal force to the structure, would be pointing which way on the left side? Down. Right? It's pointing up, so it of course has to satisfy the Newton's third law, equal and opposite on the other body, Cy, and we have fixed support here, so I'll have Ay, Ax, and a moment that I don't know yet, Ma. Right? So my unknowns, 1, 2, 3 unknowns here. Cy is fourth unknown, and dy is the fifth unknown. Total number of unknowns is 5. And equations. Equations. How many equations do I have for these two free body diagrams? 6 equations. And Seems like we have more equations, less unknowns. Can anybody tell me why is that? That's right. So we did not account for the internal x forces. So what we'll do is we'll take out the equation of sum of forces in the x direction equal to 0 here as well, because that equation essentially is saying to me right now 0 is equal to 0. Or the other way would be to put a cx pointing here, a dx pointing here, but since this is a roller, there won't be a dx, which would essentially say that the cx force itself is 0. So either way, you have 5 equations, 5 unknowns, or 6 equations, 6 unknowns. So I write it just like that: 5 equations, 5 unknowns, or 6 unknowns and 6 equations, with the hope that you understand what I'm saying here, right? The equation for the second body uh, that says sum of forces in the x direction is 0 is just a trivial equation. It says Cx is equal to 0, right? And of course, given all those 6 unknowns or 5 unknowns, we can solve for all of them. In this case, it's actually fairly straightforward. Without writing out those equations in detail, we can pretty much eyeball the solution here. This is A, this is A. Both of these need to be P over 2. So P over 2, P over 2, which means this Cy is P over 2, which means this Ay is P over 2, which means this Ax is 0. And what about the moment? P over 2 times A, right? So that's my unknown reaction. Since I can solve for all the unknown reactions, indeed, it is determinate. For the shear force and bending moment diagrams, there's a long way, short way, but if you are not comfortable with the short way, take the long way. Get the get the idea correct. Okay, so again, this is pretty much the only time that I'll take the long way to draw the shear force bending moment diagrams. But if you have a different way, then feel free to adopt that. To draw bending moment or shear force diagrams for structures like this, of course, what we do is we take cuts at different locations. So I'll have 1, 2, 3 locations that I'm talking about. For a location for a cut at 1, I would draw the free body diagram of the left or the right hand side. So this is for cut 1. I have PA over 2, force P over 2. For shear force, I'll mark it left side down, V. For axial force, again, since there's no axial force, I won't worry about it. And bending moment would be M. We can see that shear force V in this case would also be P over 2, and the bending moment M would depend upon the location X, which is the distance of that cut. So you can take equilibrium about any location, and let's see, sum of moments about the point X equal to 0 implies that minus P over 2 times X and plus PA over 2 and plus M equal to 0, which implies that moment as a distance, bending moment as a distance X would be given by minus PA over 2 and plus PX over 2, right? This is for cut 1. You can repeat the same logic for cut 2 and 3. and you can draw the shear force and bending moment diagrams. Essentially, what you should get is something like this. This is the original beams. For V, I would get P over 2, go up P over 2, go all the way across to this guy, go down by P, go back here, P over 2, and back up to this. So shear force all along the beam, all the way to the point of the load is P. Oh, sorry, P over 2. It drops down by the amount P, and then goes back up at the end. And finally, the bending moment diagram would be noting that, of course, at the right end of the roller, at the internal hinge, it should be 0. And would it be positive bending moment in the portion from B to D? Would bending moment be positive? It's going to curve like this, right? That's positive bending moment. So we'll get, it would be 0 at the hinge, positive like this, and of course they should match. And then the same line goes out here. And this amount is PA over 2. This is negative PA over 2. This is the bending moment diagram. So, so once again, what I tried to show you here was a long way to do it, or you can use certain relationships and kind of intuition combined with whatever techniques you might have learned before to draw shear force bending moment diagrams quickly, because in this course we'll be using these types of diagrams to then determine deflections and so on. Okay, so looks like I've run out of my time. We'll talk again on Wednesday, and in the meanwhile, if you have questions, feel free to drop by my office or Hui's office, and we'll see you on Wednesday.